Using suitable machinery or tools, pressure within fluids can also do useful work for us, giving us something we call a mechanical advantage. A tool or machine is said to have a certain mechanical advantage when it puts out more force than is put into it. Some machines which have a positive mechanical advantage use pressure within fluids to enable, say, a worker to move a large resistive force or load by applying only a small input force or effort. This diagram here shows two cylinders of unequal diameters connected together by a sturdy pipe. The cylinders each contain a piston. The cylinders and pipe contain a fluid connecting the two pistons. When the pistons are at rest, the atmospheric pressure pressing down on the pistons is counterbalanced by the pressure of the fluid behind the pistons. We will assume that the fluid is incompressible. By incompressible, we mean that the volume of the fluid does not change under pressure. This means that the pressure within this incompressible fluid is the same throughout the fluid, and this equal pressure acts on all surfaces in contact with the fluid. We may assume then that pressure is transmitted instantaneously throughout the fluid. You will see how important this property is a little later on. A force which we will call F1 is applied downwards on the smaller of the two pistons. This force will cause the piston to exert a pressure on the fluid underneath it. The pressure exerted because of F1 is extra to the atmospheric pressure already acting on the piston. This extra pressure will be equal to the force F1 divided by the area of the piston. We will label this smaller piston and its area A1. Let's put some actual figures to the forces and areas. We will assume that F1 has a magnitude of 10 newtons, and that the area of piston A1 is 0.05 square meters. The surface area of the larger of the two pistons, A2, is equal to 0.2 square meters. Note that this is 4 times the surface area of the piston A1. Using our pressure equation, we calculate that the pressure exerted on the liquid by piston A1 is 10 newtons divided by 0.05 square meters, giving us a pressure of 200 newtons per square meter, or 200 pascals. Piston A1, therefore, exerts a pressure on the liquid of 200 pascals in addition to atmospheric pressure. This additional pressure is transmitted to all parts of the liquid, so that the liquid exerts this pressure against any of the surfaces with which it is in contact, one of which, of course, is piston A2. If we now rearrange the pressure equation to make the force the subject of the equation, we can use the equation to calculate the force generated by a given pressure acting on a given area. Here, a pressure of 200 pascals is acting on piston A2 in addition to atmospheric pressure. So the force generated at piston A2 equals pressure multiplied by the area of piston A2. The force generated at piston A2 then is 200 pascals, or 200 newtons per meter squared, times 0.2 meters squared. So the force generated at piston A2 is 40 newtons. Therefore, we can see that by pressing down on the smaller piston A1 with a force of 10 newtons, the larger diameter piston, A2, pushes upwards with a force of 40 newtons. That's 4 times the original force. So you can see intuitively that the mechanical advantage of this machine is 4. And you can probably deduce that we calculate the mechanical advantage by dividing load by effort. That is, by dividing the output force by the input force. This machine, for example, enables us to lift a load of 40 newtons by making an effort equal to 10 newtons, so its mechanical advantage is 40 divided by 10, which is 4. However, there is one principle involved here that it is very important for you to understand. Though it is possible to get more force out of a machine than the force we put into the machine, we cannot ever get more work out of a machine than we put into it. So even though piston A2 pushes upwards with a greater force than that applied to piston A1, this greater force can still only do the same amount of work as the work done by the force applied at piston A1. Now, work done, as you may remember, is equal to the size of a force times the distance through which the force moves. You can probably work out intuitively then that if piston A2 pushes upwards with a greater force than that applied to piston A1, the distance moved by piston A2 must be smaller than the distance moved by piston A1, because the work done by both pistons has to be the same. In fact, if we do the maths, we will find that in order for the work done by both pistons to be equal, the distance over which piston A2 rises must be a quarter of the distance that piston A2 is pushed down. Let's work out an example. We'll assume that the force of 10 newtons moves piston A1 through a distance of 4 meters. Now, we already know that piston A2 pushes upwards with a force of 40 newtons. Because we know that the work done by both pistons is the same, we can easily calculate the distance through which piston A2 rises. So 10 newtons multiplied by 4 meters equals 40 newtons multiplied by d2, the distance moved by piston A2. This gives 40 joules equals 40 newtons times d2. Therefore, the distance through which piston A2 rises must be equal to 1 meter. That is, a quarter of the distance travelled by piston A1. You should know that the branch of science and engineering which deals with the transmission of force through liquids in order to do useful work is often referred to as hydraulics, from the Greek word hydra, meaning water, and the Greek aulos, meaning pipe.